We have seen earlier also about what are minimum and non-minimum phase functions. Here we are going to dig a little bit more deeper. Those linear and time invariant systems which are having all their poles as well as zeros lying in the left half of S-plane are referred as minimum phase transfer functions. This is the definition which will be very helpful for you in the subject control systems. But the more important definition is the second definition, which is minimum phase transfer functions are those transfer functions which, along with their inverse functions, are both causal and stable. We will be studying about what are causal and stable in great depth in the subject signals and systems. But this is actually the proper definition of what are minimum phase transfer functions. This word stable is actually very important. It simply says that the minimum phase transfer function as well as its inverse function cannot be marginally stable also. So, in other words, poles as well as zeros on the imaginary axis are also not allowed for the systems to be a minimum phase function. There is one condition for minimum phase function, which is when we try to find the phase of the transfer function when the angular frequency tends to infinity, then the phase angle will come out to be equal to the number of zeros minus number of poles multiplied by 90 degree. But there are few examples where this condition will be valid, but still the function is not a minimum phase function. Let's see an example. I have taken a random function which is equal to s multiplied by s plus 1 divided by s plus 3 into s plus 5. For a frequency response, its equivalent frequency response can easily be found, and after that you will get the phase of the transfer function to be equal to 90 degree plus tan inverse of omega minus tan inverse of omega divided by 3 minus tan inverse of omega divided by 5. Now if we try to find the limiting value when the angular frequency tends to infinity, you will get phase is equal to 0. Again, if we try to verify it through the formula, then also we will get 0 degree. But still, even though this condition is verified by the system is still non-minimum phase function, because as you can see, there is one zero which is present on the imaginary axis. The reason behind why zeros on the imaginary axis are not allowed is very simple. See, our main objective is to find a stable system. Even though the considered transfer function is stable, but if we are going to take its inverse, then the pole of the transfer function will become the zeros of its inverse function. Similarly, the zeros of the transfer function will become the poles of its inverse function. Since for the considered transfer function, there is one zero which is present on the imaginary axis, so its inverse will have a pole present on the imaginary axis, which will make the inverse function to be a marginally stable system. That's why zeros on the imaginary axis are also not allowed. If the open loop system is minimum phase system, then for closed loop system to be stable, both the gain margin and phase margin has to be positive. There are few methods for analyzing the frequency response, which are Nyquist plot, polar plot, as well as Bode plot, which you are going to study in later lectures. However, Bode plot analysis is suitable only for minimum phase transfer functions, whereas Nyquist plot method is suitable for minimum and non-minimum phase transfer functions. Similarly, we are having non-minimum phase transfer functions. Linear and time invariant transfer function to be a non-minimum phase transfer function should have at least one pole or zero on the right hand side of the S-plane or on the imaginary axis. If open loop system is non-minimum phase system, then for closed loop system to be stable, both gain margin and phase margin should be negative. There is one more very small topic, which is time delay system, which is also referred as transportation lag system. The general form of transfer function of a time delay system is equal to natural logarithm e raised to the power minus st, where the sinusoidal form of our transfer function can easily be found, which will come out to be equal to cos omega t minus j sin omega t. You can easily find magnitude of this transfer function to be equal to 1 and phase to be equal to minus omega t. The transfer function then can be represented in the form of amplitude and phase, which will come out to be equal to 1, providing phase shift of minus omega t. Here, omega t is in radians. If we have to convert the omega t in degree, then we have to multiply it with 57.3 degrees. Before you move forward to the next unit, which is root locus, let me clarify one thing. Generally, root locus is taught before the frequency response because root locus is actually a method of time domain analysis, but I have rearranged it slightly because for competitive exams, gain margin and phase margin is very important, and sometimes very good questions are framed by merging the topics of root locus and gain margin. So for better understanding, I thought it will be better if I teach frequency response earlier than the root locus. Now try to answer a very simple question, which is, which of the following is not a frequency domain analysis method? I just told you that root locus is a method of time domain analysis. So the answer will be the V option.